let's see how the fluid temperature changes in heat exchangers, and particularly for a double pipe heat exchanger. Let's say this is the heat exchanger that I am looking. So we have hot stream, hot fluid, and for the parallel flow, this is the cold. That is going out from the heat exchanger, and let's assume the cold comes with this Tc and I, and we have m dot of cold, Tc of out, and then this is Th and I, Th and out. If I look at the temperature profile for this system, so this is the parallel or co-current flow. Now, if this is temperature, this is X, this is, let's say, let's call this one point inlet as a 1, and this is at point 2, so I'm just going to call it 1, and 2 along the length of the heat exchangers that we have, and let's say this is L for the length of the heat exchanger. So the hot stream gets in at the Th and I, and it loses the temperature, goes out at Th and O, and the cold stream Tc and I gets in, increases temperature, and goes out at Tc and outlet. This is going to be the way that the fluid temperature is going to change. So for the hot and for cold. Now, if I look at the counter flow, same thing. Say I have the heat exchanger. So let's say we have the hot flow just going this direction, and the cold stream in that direction. So here, if I plot for this counter current flow, Ex, and let's label that one. This is Th and I, Th and O, TCI, TCO, and this one 1 and 2, and let's do the plotting for the length of that 1 and L, and let's say this is 0.2. So the hot stream gets in, loses the temperature, and the cold stream comes from the other side and gains some temperature. So this is Tc in, Tc out, Th in, Th out. So this is going to be the temperature profiles that is changing along the length of these heat exchangers for the parallel and the counter flow. Now, the other things that we would like to see here is the amount of heat transfers that's happening here. So if I write the heat transfer for one fluid, let's say this hot fluid is just changing the temperature from I to O, Thi to Tho, then I can write down Q for the hot stream is going to be minus m dot H Cp of H, assuming the Cp is constant or we are taking an average value for that one, THI minus THO. I'm putting the negative because it's just losing the heat. I can write the same Q is getting gained by the cold flow, so it's gonna be equal to m dot C CPC TCI minus TCI minus TCO. So this is gonna be the amount of heat that each of these fluid, this is the hot fluid is losing, and this is the cold fluid that is gaining. Now the overall heat transfer coefficient, the overall heat transfer from the hot to the cold. So they're gonna be this Q that the hot stream is losing is just get transferred to the colder one. So I can write Q based on the overall transfer coefficient, a surface area that's providing, and some average temperature difference. I'm talking about average temperature difference because the delta T, so this is, let's say, delta T1, or at the outlet, if I call that one delta T2, this delta T is keep changing from one location to another one. And we are looking to find out what would be this average delta T that's happening here. For doing that, let's assume we are looking for a small element of this heat exchanger that has a dA, and you're looking at the dQ, the heat transfer that's happening in this small element. So at this small element, if I just call this temperature difference dTH, this is the temperature loss, and for the cold flow, let's call that the difference in this element that happened is dTc. So I can write for dA, I can write the energy balance equations, and for the hot stream, this dQ is gonna be minus m dot H CPH dTH, and for the cold stream is gonna be m dot C CPC dTc. So this is gonna be the heat transfer by the energy balance that we are writing, and we call this term like m dot C as C of H for the hot stream, capital C dT C dTH, sorry, and call this one the hot stream heat capacity rate. So for the cold stream, this is going to be the heat capacity rate. So this is going to be equal to C capital C etc. I'm just going to make this one small c so we don't get confused. Okay, so this is the heat transfer loss and gain by the hot and cold stream as they are passing through this dA. Now the heat transfer, like from the hot to the cold, the rate of transfer across the surface area dA can be expressed as dQ is U TH minus TC dA. So remember, I'm assuming that this is a very small element here. So I can say, like, I can put an average value for TH and TC here. And I can write down based on that one. Now, from here, from these two equations, what I can say here is dTh is dq over minus m dot h cph, and dTc is dq over m dot c cp and c. And if I write dTh minus dTc from the above, it's going to be minus dq 1 over m dot h cph plus 1 over dot c cp and c. So this is going to be the difference between them, and I'm going to use what we have written here for the dq and replace it here. So this is going to be equal to u th minus tc over m dot h cph plus 1 over m dot c cpc times dA. So if I just bring all the temperature in one side and do the integration, so what we have here, we have d of th minus tc, that's these two terms, divided by that, which is th minus tc, is equal to u minus u. 1 over m dot h cph plus m dot c cpc times dA. So if I take the integral of both sides from inlet to outlet from point 1 to point 2, then what we are going to get here is, and assuming that th minus tc is delta t, by taking the integral, what we are going to get is natural log of delta t2 divided by delta t1 equal to minus ua 1 over m dot h cph plus m dot c cp and c. And we know that from the energy balance that we were writing from the beginning, we can find out the values of this m dot c, which is q over delta h. So here, I'm going to say recall m dot h cp and h is q divided by thi minus th and o, and m dot c is q over tco minus tci. Now, if I just replace them here in the above for these two terms and rearrange the equation, q is going to be ua delta t2 minus delta t1 divided by natural log of delta t2 divided by delta t1, which is ua delta t lm. And this is for the parallel flow. So this provides a sort of average temperature here. Consider that this delta t lm, which we call it log mean temperature difference. So this is log mean temperature difference is going to be delta t2 minus delta t1 divided by natural log of delta t2 divided by delta t1. So this is for the in general, and we looked at the parallel flow, and for parallel flow delta t2 was tho minus tco, and delta T1 was THI minus TCI. I'm just looking at the point 1, the temperature difference, and point 2, the temperature difference here that we have. This log mean temperature difference is actually an average temperature and act as a driving force for the heat transfer that can happen. A similar analysis can be used to show the same results is valid for the counterflow. So for counterflow, this is for parallel flow. For counterflow, we can get exactly the same definition of LMTD, but what we have is delta T1 is THI minus TCO, and delta T2 is THO minus TCI. So if you look at that, yeah, this is the difference. This is delta T1, and this is delta T2 that we have. A couple of other points about this LMTD is if in case of counter current flow, so if we have a counter flow where m dot h Cp and h is equal to m dot c Cp and c. If you look at the temperature profile for this case, what you would notice here is this is Tx 0.1 and 2, and this is for the length of that. So let's say this is the hot stream, THI, THO. Now, the cold stream entering at TCI, the delta T across that is going to be exactly the same. So everywhere, this is going to be the delta T. So there is really no change in that. So this is going to be TCO. So for this case, when we have a counterflow and the m dot c for both cases are the same, then what we are going to see here is delta T1 is equal to delta T2. And if you use the definition of delta TLM, it's going to be equal to delta T log mean. So this is for the case of counterflow. Let me just put the arrow here so it shows that one. Now, the other thing is if condensation happens, condensation occurs at constant temperature. So really the site, whether it's in the tube or in the shell, the temperature is not gonna change. And the other things that condensation is characterized for practical applications in design of heat exchanger, m dot h, Cp and h, can assume goes to infinity. Now looking at the temperature profile, what we are gonna see here is a constant temperature, and doesn't matter really from which side the flow is getting in. So this is 0.1, 0.2. But for the cold temperature, what you're going to see, the increase in the cold temperature. So the temperature does not really change. So this is T and X for the length of the system. The other one is for the boiling or evaporations. So let's say if we have a boiling will also occur at constant temperature. And again, for practical application, m.c, Cp and c is going to go to infinity, and the temperature profile for the case that we have boiling is going to be constant temperature between 0.1 and 2 for the length of heat exchanger, and the hot stream is going to just lose heat. So this is going to be for the hot stream. Now, what we developed for the LMTD, or this driving force or average temperature as a driving force, was for the double pipe heat exchanger, okay, for the parallel flow and counter flow. Now, At the beginning, we discussed that we have other type of heat exchanger like multipass and cross-flow heat exchanger. We cannot directly use LMTD, but the way that we use, we bring a correction factor F. So we use LMTD with the correction factor F. So the way that we write it, we write in the modifier form Q is UA. This correction factor, let me just put it in a different color, delta T log mean. Now the value of F, it really depends on the number of tube passes and the number of shell passes and other configurations design, and generally we can find it in the chart. Now F is 1 for double pipe, as we saw for double pipe heat exchanger. Again, we can consider F as 1 when we have condensation or boiling, when boiling condensation involved, and F gets values less than 1 for other type of heat exchangers that we can obtain, can read it from charts based on the type of heat exchanger that we are dealing with.